Very good afternoon to each and everyone present over here. So today we are going to start with the new topic, which is the general part of the organic chemistry, which is isomerism. We'll discuss what exactly isomerism with the help of a definition of it. So we know that those functional groups, like if we have some formula, so for compounds, they are having the same formula, but their chemical structure is different. If we take the example of aldehyde and ketone, because in aldehyde, CHO moiety is present, and in ketone, C double bond O moiety is present, where the number of hydrogen can differ. So that is how the aldehyde and ketone are known as structural isomerism. So there are different types of isomerism, which we'll discuss. So isomerism do not necessarily share similar characteristics. Like if I just discussed about the aldehyde and ketone, so they might not be having the similar chemical or physical properties, but two main forms of isomerism they can or they cannot have. So two main forms of isomerism, structural or constitutional isomerism, in which bond between the atom differ, and stereoisomer or special isomers, in which bond are the same, but the relative position of the atom differ. Okay. So in structural or constitutional isomerism, just there is a change in the structure. Okay. So here is the total classification on which isomerism has been classified. So like over here, isomers are defined into constitutional isomers and stereoisomers. Now stereoisomers are of two types, diastereomers and enantiomers. Diastereomers are further divided into two types, cis and trans. Okay, so cis isomers are those which have the functional groups on the same side. Like over here, the methyl group are on the same side, whereas in the trans isomers, the methyl groups are on the different position. Okay, so like this, these are the trans. Okay, cis are those isomers in which the same functional groups are present on the similar side of the atom. Okay, then diastereomers can be conformers and rotamers. Rotamers are like this. Okay, so like this is the chiral carbon, which is attached to four different groups. Enantiomers are non-mirror images of each other. Okay, so enantiomers are non-mirror images of each other. When you overlap these structures, they will not be able to overlap. Then constitutional isomers or structural isomers, as we look over here with the help of the example. Like fluorine is attached to the second position in the first structure. So this will be 2-fluoromethane. And in the second structure, it is 3-fluoromethane. So there is a change in the structure. This is what is called as structural isomers. Okay. Now, what exactly is isomer? The English word isomer is a back formation and which is borrowed from the German word or a Swedish word, which in turn was coined from Greek with roots iso means equal. Equal parts should be there. That is what is called isomerism. Now we talk about the structural isomers. They have the same number of atoms. The structure is different. Okay. The molecular formula is same, but the atoms are connected in a distinct way. For example, there are three distinct compounds with the molecular formula. Over here, I mentioned with the phenol, first group is hydroxy, second is hydroxy at the second position, secondary alcohol, and third one is ether. Okay. So the first two isomers shown are propanols. Okay. These are propanols because these are structure of alcohol. And these are derived from propane. Both have a chain of 3 carbon. Okay. So like they are having a chain of 3 carbons and connected by a single bond with the remaining carbon valences being filled by 7 hydrogen. Okay, like over here, 3 and 3, 6 and 7 hydrogens are there because the valency of the carbon has to be satisfied. And then comprising of an oxygen atom bound to a hydrogen atom. So these two isomers differ on which carbon the hydroxyl group is bound. Okay, so in the first case, the hydroxyl group was at the first position. In the second, it was on the second position. But in the third formula, where like if we discuss about the propane 1-ol, which can be called as propyl alcohol or n-propanol, or in the so good afternoon each and everyone. So today we are going to discuss a new topic of organic chemistry, isomerism. So isomerism is actually what? It is when the similar structure is there, like chemical formula is same, but the structure is different. We talk about the case of aldehyde and ketone, in which aldehyde and ketone are having the same molecular formula, but the chemical structure is different. Isomers do not necessarily share similar chemical or physical properties. Okay. So it's not necessary that the chemical or physical properties should be same. They can be or they cannot be similar. Two main forms of isomerisms are structural or constitutional isomers. Structural isomers are those which have the similar structure or constitution in which the bonds of the atom have similarity and but they differ in each other. And stereoisomers or special isomers in which the bonds are same but the relative position of atom differ. Is the isomer classification, where we can classify them as constitutional and stereoisomers. The constitutional isomers are those which differ in the structure. Like over here, the fluorine was attached at the second position, and here the fluorine is attached at the third position. So this is two fluoromethane, and this is one fluoromethane. Stereoisomers, on the other hand, are special isomers. This can be defined into distereomers as well as enantiomers. Distereomers are again further classified into cis and trans isomers. Cis isomers are those Okay. So cis isomers are those which have the same structural group attached at the on the same side, whereas on the trans isomers, like this methyl group trans to butene, if we talk about, then the two methyl groups are attached on the different position. Now we talk about the enantiomers. These are the non-mirror images of each other. Like if we superimpose these structures, then they won't be able to give a mirror image. Then diastereomers are again classified as conformers and rotamers. These are the conformers and rotamers of the similar structure. Now, the English word isomer has been derived from the German or a Greek word, where the roots are isos, which means equals, and meros means part. So isomers are of equal part. Just now we discussed in the definition that they have the same chemical formula, but their chemical structure can differ. So first of all, first we come to the structural isomers. So structural isomers have the same number of atoms of each element. Okay. So if we say about the structural isomers, means they have the same molecular formula. Okay. But the atoms are connected in distinct ways. Okay. Like, for example, here I've taken the example of propane 1-ol, propane 2-ol, and ester, ROR, which is ethyl methanoate. Okay, so in the first case, the alcohol has been attached. In the first two isomers of propanol, the alcohol is derived from the propane basic ring. Both of them have a 3-carbon chain, atoms connected by a single bond, and the remaining valencies of the carbon are satisfied by hydrogen attached to them. So the two isomers differ on which carbon the hydroxyl is bound to, either to an extremity of the carbon at the first position, which is propane 1-ol, which can be called as 1-propanol, N-propyl alcohol, or N-propanol, or to the middle carbon propane 2-ol or 2-propanol, isopropyl alcohol, or isopropanol. These can be described by the condensed structural formula, which is mentioned over here. But the third isomers, which is ether is methoxyethane. Why this is methoxy? This one is methoxy because methyl group is attached to ethane. Two bonds are there. That is why it is methoxyethane. Unlike the other two, it has the oxygen atom connected to the 2 carbons and all 8 hydrogen bonded directly to the carbon. And this is what the ether group is. ROR, ether, methoxyethane or ethyl methyl ether. So the alcohol 3-propanol is not another isomer, since the difference between its 1-propanol is not real, because 3-propanol and 1-propanol will be the same thing. It is only the result of an arbitrary choice in the ordering of the carbon along the chain. For the same reason, ethoxymethane is not the another isomer, because this will remain the same. If you say that ethoxy and then methane, so you are just changing the priority, like ethoxy you are giving, Along with taking this oxygen and methane, you are taking as an individual moiety. Okay, then 1-propanol and 2-propanol are examples of positional isomers because the position of the hydroxy group or the alcohol has been changed, which differ by the position at which certain features such as double bond or functional groups occur on a parent molecule, propane in this case. Now we comes to the tautomers, which is again a type of a different isomer. So tautomers are those structural form isomers which readily interconvert so that two or more species coexist in equilibrium. Now we'll ask, what is equilibrium? So equilibrium is a thing where the two can interconvert readily. Readily means like this bond has been formed. So YZ form can be readily interconvert itself to XY form. These amino acids. Now resonance forms. Resonance form. The structure of some molecule is sometimes described as a resonance. Okay, between several apparently different structural isomers. The classical example is 1,2-dimethylbenzene or orthoxylene, which is often described as a mixture of two apparently distinct structural isomers. 1,2-dimethylbenzene is at the second position and orthoxylene. However, neither of these two structures describe a real compound. That is to describe by their averaging or resonance. Thus, the delocalized bonding of orthoxylene, which is the single isomer with benzene core and two methyl groups in adjacent positions. So, if we see over here, resonance means the interchanging of the double bond which exists. So, here, if I shift this double bond, the position of this double bond, when I will change like this, then this is what is called as 1,2-methylbenzene, which has changed its position orthoxylene so as to form its structural formula. Okay. This is what is called resonance, the interchange of the position of the pi bond, doubly bond between the carbon, they interchange their position so as to form the resonance, which is quite very stable. However, neither of these two structures describe a real compound because the interchange between the two resonating structure is very fast, and that is why we averaged the resonance, because the actual delocalized bonding of orthoxylene, which is the single isomer with a benzene core and two methyl groups in the adjacent position. So we took the average of these both structure because the resonating structures cannot be defined. Now comes to stereoisomers. Stereoisomers are those which have the same atom or isotopes connected by bonds of the same type, but differ in their shape, the relative position of those atoms in space apart from rotation and translation. Just now we see about the cis and trans isomers, in which if the same functional group or moiety, methyl moiety or any other group has been attached at the same position, then it is called a cis. And when it is attached at the different position, opposite position, then it is called as trans. So if we talk about the molecular model of cyclohexane in boat and chair form, the carbon atoms are colored amber or blue color according to whether they lie above or below the plane. Okay. So of the ring. So CC bond of the ring are light green. So these are the bonds and these are the above the plane, and these are the below the plane. So these bonds shows the boat and chair conformation. Now comes the conformational isomer. It is an arrangement of an atom of the molecule or ion for which the internal energy is local minimum. This arrangement, such as any small changes in the position of the atom, will increase the internal energy. and result in force that tend to push the atom back to original position. Like this, one can imagine any arrangement in space of the atom of a molecule or ion to be gradually changed to any other arrangement in infinitely many ways by moving each atom along an appropriate path. However, changes in the position of the atom will generally change the internal energy. Okay, so we have to choose a path where the minimum energy has been associated, which is determined by the angle between the two bonds. Okay, bond angle will determine the distance between the atoms. If the bond angle is large, then the distance between the two atoms will be large. Next, we come to enantiomers. Two compounds are said to be enantiomers if the molecules are mirror images of each other. Okay, so mirror images of each other, they cannot be made to coincide only by rotation or translation. Okay, so these are the mirror images of each other enantiomers, and they cannot be made coincide only by the rotation or translation, like a left to right or right to left. These two shapes are said to be chiral. Now, what is chiral carbon? Or any atom which should be chiral is when it is attached to four different moieties. Okay, so if I am making the enantiomers, two compounds are said to be enantiomers if they are attached to four different moieties in such a way that their mirror images are overlapping to each other. Okay, and but the overlapping cannot be made into coincide. Okay, the overlapping cannot be done because uh, only by the rotation or translations. Okay, if they're left to right or right to left, like it is moving clockwise or anti-clockwise, then only the rotation or translation can take place. Thank you. In the next lecture, we will cover the more examples of the chiral and non-chiral compounds, carbon compounds, and various stereoisomers, structural isomers, and conformers. Thank you.